Okay, so now let's start talking about aircraft structures, how they're built, and what they're made out of. In order to do this correctly, we really need to start with the basics and get back to just understanding the materials that we're going to be working with and that the aircraft we're going to be responsible for are built from. Now, early on, if you go back and watch the video on like aviation heritage, you'll know that early aircraft were made to no real set standard, no real set design. People were just experimenting. And in those days, in those early days, even back to the 1700s, the easiest, most pliable material that the everyday man had access to was wood. A lot of times it was wood and fabric. So early aircraft were built just like that. They were built with these longerons made out of different types of wood. Eventually, like we would get into like the really light woods, like balsa. You might have built balsa wood models before, and you still can. You can still order them that way. But they would build the structure out of wood, and they would wrap it with cloth. A lot of times a type of linen, eventually canvas, and then to preserve it, they would dope it up. Now, those aircraft are still around, and aircraft designs like that, like say like the Piper Cub, the original J3 Cub, or I guess different emulations of the Wright Flyer. They're still around, but they're a very, very niche, very, very specialty part of aviation. And mostly it's done to just kind of preserve the heritage and not really used for any sort of practical purpose. So we won't really be spending any time on how to detect wood rot or how to dope things or how to cover an aircraft with canvas or anything like that. Thanks to the new rule changes, we don't have to cover those types of things. And you'll never probably see them in your career unless you just steer yourself that way. So let's get on to other types of materials. Now, the way we're going to progress through this is we're going to start with the more niche-y types of materials, and then eventually get into metal, and then we'll get into like how metal is made and all the cold working and metalworking processes that go into that. I love on movies whenever something comes through an airplane's window and it shatters like glass. It always cracks me up because you know what? They're made of plexiglass, a type of plastic that's translucent that you can see through. Now, this is pretty standard for most aircraft, especially a general aviation aircraft. Once you get into some of the more advanced, heavier aircraft, you'll get into different types of materials. But for the most part, it's all plexiglass. And the reason is simple, it's flexible. If you have a bird strike or something hits right here, you'd rather it give way and dent in rather than break and shatter and turn into a million daggers flying at you, or even safety glass with stuff flying around. Then on top of that, you have to contend with the wind. Even if you make it through the initial crash, you end up having to take a 200-mile-an-hour wind directly in your face while you're trying to operate something that's thousands of feet off the ground. So it's a lot better to have something that can flex, that can push in, rather than anything else like that. Now, this is an example of how plastic gets used on aircraft, and it's susceptible to certain things. You notice all this dust on here? It'd be very, very tempting to come up to an aircraft and just wipe it off. That will scratch it to no end. Now, in the worst possible way. You won't even necessarily see the scratch early on, but what will end up happening is that you'll get into a low light situation or some kind of like weird angle, and all of a sudden all those little scratches will reflect back into your eyes, and you'll realize how much you just damaged the visibility looking outside of that plane. So what you want to do is take water and pour it down and let all the dirt kind of go off, and then wipe in a single direction. So at the very least, if you do scratch anything, it's straight up and down and not sideways. But we'll get into that more whenever we start talking about aircraft washing. For now, just know that plastic is a very common material that gets used throughout all of an airplane. Another very common material that you'll find on aircraft is rubber. Rubber is used obviously in tires, but also on hoses and other things as well. Sometimes you'll even find them inside of fuel cells. So sometimes on like a Cessna 210 or an OH-58, you'll have fuel bladders. Sometimes those are rubberized. They naturally don't want to, they want to get rid of oils, and they're kind of naturally repellent of a lot of different chemicals, and so they become, you know, a kind of a go-to material to start building. Now, a lot of the natural rubbers can be found on certain aircraft tires, but there's a lot of synthetic rubbers that are out there nowadays too, and it's probably more common to find synthetic rubbers than it is to find natural rubbers. And we won't get into the details, and you can read more about it in the 8083. There's tons of details about rubber if you're a materials drawn kind of individual. But just know that rubber is something that you'll find on a pretty common basis. And we're going to build, rubberized, hoses here before too much longer. So rubber is something that you're going to come into contact with fairly frequently and fairly soon. Another common material that gets used on airplanes is fiberglass, or any sort of type of composites. Now, composite gets its name because it is a composite of things. So, meaning it's multiple layers. Sometimes composite can be like our tap tester that we looked at in the last video with the FLIR gun. It is carbon fiber with a foam core and carbon fiber on top of that. It's a very common type setup. Another type of composite you may have is multiple layers of carbon fiber with an aluminum honeycomb core, or even an acrylic or a Kevlar honeycomb core that's layered with carbon fiber on top of that. That's also very common. That was very common in the OH-58 that we used to work on. Nowadays, composites are being used more and more and more and more, to the point where whole aircraft are being built out of carbon fiber as opposed to aluminum or any other type of material. So for instance, the 787's entire fuselage is spun carbon fiber. The 737 MAX has chunks of carbon fiber on it. The 777X, carbon fiber. There's even kit planes now being built by Dark Arrow that are all carbon fibers. And they're not necessarily anything new. Composites have been around for a while. Burt Rutan back in the 1970s and 80s were selling kit planes for like the Long Easy, the Cozy, that were all carbon fiber planes. Now, or all composite planes. They were, fiberglass or e-glass back in those days. Now, they have a lot of advantages. They're extremely strong. They're very, very, very strong. And they're extremely lightweight. The thing that holds a lot of aircraft from being built by carbon fiber is the manufacturing process is very, very difficult. And so it leads to higher cost. And so it doesn't become economical to build production aircraft like that on scale. But for onesies and twosies, and one off here or there that have like a lot of deep pockets, well, carbon fiber becomes the way of the future, or composites become the way that they get built. Essentially, you take a mold and you were to place your fabric in a mold, and then you place resin on top of that, and you let it set up, and then you pull the mold away and you have a part. That's how basically all composite materials get made. There's 3 ways to kind of go about it. Just like you have what's called a wet layup, and that's literally what we just described. We have a mold, we put our fabric down, and we dope on resin, and we let it set up. It's pretty easy. Another one is a wet layup plus a vacuum bag, and so you would do the same thing, but this time you put a vacuum bag on top of it and you suck it down. And what that does is it squeezes out all the extra resin off to the sides, and also it helps impregnate that resin into the fabric. So you get a better part, and it's also lighter weight because you're using less resin. The last one, to kind of technique to build them, is through infusion. So essentially it's the same process, except for you vacuum bag down your part till it is extremely vacuumed. I don't know what the right adjective there is. And then you introduce the resin into that vacuum. Same way you would charge, like, say, an HVAC system on your car or in your house or whatever. So for this time, you're charging a part with resin, and it basically, that vacuum sucks all that resin in over the course of a 24-hour period. And then you put it into like an autoclave, or you just let it sit and cure room temperature. and it sets. And that's the best way to actually build parts. But these are all composite approaches that are the way of the future. Eventually, you'll see less and less and less aluminum being used on aircraft as the manufacturing process becomes more and more standardized, more and more streamlined, and therefore lowers the cost to do more and more of it. You can accomplish a lot of the same types of strengths you can with metal for a fraction of the weight. And the way that sustainability is playing such a major role in manufacturing and aircraft production and operation, you can only guess that this is going to continue to be the case in the future. So it's something that you really need to know about. Now, if carbon fiber or composites are really all that in a bag of potato chips, why are we using it all the time? Well, even though it's super lightweight, very, very strong, easily repairable, it does have some drawbacks. For one, it doesn't do well, especially carbon fiber, with lightning. It will literally explode. And so like in some composite panels on some of these bigger aircraft, the way they get around that is they essentially take a wire mesh and they use it as part of the layup. So whenever they're taking their fabric, another layer of fabric, then they'll put this wire mesh in there, then fabric, wire mesh. And that basically creates a Faraday cage around the aircraft. So whenever lightning strikes it or some sort of electrical discharge happens, instead of getting an explosion, you get the electricity dispersed out the static wicks and everything is fine. So that's one danger for it. Number two is, even though it's easily repairable, it can be extremely toxic. Carbon fiber dust is a cancer-making machine, and you don't want to ingest that into your body. So whenever we're working with it here, we'll end up putting a lot of personal protective equipment on. But that's another detractor, is that you don't necessarily want to have to repair it, because as you cut it and as you put all that dust in the air, there's health effects that could happen or that you don't want. All right, so let's talk about some forces that get placed on metal and other parts as well. First off is tension. That is the force that tries to pull things apart. So anytime that you see tension going, it's trying to pull things apart. Now, you wouldn't believe it, but actually the wing a lot of times will be under tension. All right, if the wings want to flex up, that means that the bottom parts of the wing are being pulled apart. And so that's something that we need to take into consideration with design and material selection, is that tension is being happened. Compared to compression, is that is the force where things are being pushed together. So back to our aircraft, the wing is being, if the wings or it's taking off, it's full of fuel, and the wings are coning up like that, well, that means that the top are being compressed. And you'll see these stressors on aircraft as you watch the wings flex. Helicopter blades is a really good one. Anytime that they pull pitch, you'll see the blades cone up. That's tension and compression being balanced out right there. The other one, torsion or torque, is the amount of twist that's being placed on an object. Now, torque is the amount of twist that's being placed on an object. In the last class, we talked about torquing a bolt. You're placing torsion or torque onto an object that way. When they talk about like the amount of torque a car has, that's the amount of twist that's being placed on the drive shaft to help turn the wheels via the differential and the axle. So when you hear torsion, you hear torque. Now, it's not nearly as pronounced, but there's actually torsion on the fuselage itself through an asymmetry of lift. As the plane goes through there, you're going to see a greater weight of air pressure being placed on one side, resulting in what pilots will know as P factor. Well, that as you correct it, as you try to come back this way, and the tails would trying to pull you the other way, you're contorting the fuselage that way. It's not nearly as strong as the compression and tension factors in the wings, but it's still a factor. A anti-torque rotor on a helicopter is there to counteract the torque of the main rotor. When we get to helicopter aerodynamics, we'll talk about this a lot more, and helicopter rigging, we'll talk about it a lot more. But essentially, main rotor torque is a key performance factor that you're watching in the cockpit as you're pulling pitch. You want to make sure that the main rotor is not over torqued, because you'll strip out the transmission. All kinds of other bad things will happen. But the way that you counteract that torque that you're watching is through the tail rotor in the back. As it pushes air off to the side, it is using that force to counteract the torque of the main rotor on the airframe. So it's torsion. Okay, so bending is another, a way to describe the balance between the compression on the top of the wing and the tension on the bottom of the wing that causes the wings to bend, and that's just simply an object that's being moved by these forces. Main rotor blades coning is another good way to think about bending. Bending, it shouldn't be anything earth-shattering. You've been bending things your entire life. Just simply like by pushing up on the outside and down on the inside of this magnet. I don't want to mess it up, so I'm not going to do it too much. But that's the bending force. Okay, one that's a little bit more difficult to explain with our little airplane or our magnet here is shear force. So I'm actually going to use 2 credit cards. Let's see here, my debit card and my driver's license. Okay, so shear forces are simply like these 2 cards sliding side to side. That force that you're hearing there is the result of the friction between the cards that are coming from the shear force of those 2 cards. So when you think about wind shear, what's happening there is the plane's flying along and it's in one body of air, all right? And so let's say it's transitioning up, and this air is going this way, and another mass of air might be going that way. And as you cut through that turbulence and you're bouncing around, if it's really, really strong, you get into a situation where you have wind shear, that the front half of the plane is being pulled this way, and the bottom half of the plane is being pulled that way, causing it to want to do that number or break apart. There's been a few aircraft that have gone down because of wind shear, but it's very, very, very rare. I think it's only once or twice. But that is a force that we need to be aware of. Primarily for our purposes, it'll be thinking about mounting 2 parts together. You'll have a shear force. You might have shear bolts in certain places to keep things from moving back and forth. And so, yeah. Okay, so strain's another one that you'll think about. Think about bending. If I bent this and I really bent it hard, it would turn into a banana and it wouldn't work anymore. And that would be an example of strain. When they load test a new aircraft, they're going to put a bunch of weights on the wing and see what happens whenever it bends down. And they're going to get to a certain amount of poundage for a certain amount of time and let it sit there. And then the next day they'll come and they'll take all these sandbags off and see if the wings pop back up. If not, it shows that they have a design flaw or a material choice flaw that they need to correct, because the aircraft is not up to the strain of flight. And usually it's way more than what they'll ever actually experience in flight, but it's a safety factor thing. So that is strain, the amount of strain on there. You're going to see strain all over the place. One of the things that you'll mainly be doing NDI and NDT for is the effects of strain. So the story I told in the NDT class about the OH-58 tail rotor gearbox wanted to pop off, that was a strain failure. The fuselage or the tail rotor gearbox kind of set like on the tail boom, and it was always wanting to pull up like that and go off because the excessive force is being placed on it from the enhanced tail rotor. That popping force that's wanted to happen like that over time overstrained the metal, and then eventually it fatigued out and gave way. This isn't just in aviation. You'll hear about bridges being fatigued and the bolts, kind of giving way, or metal cracking. You see it in cars. Just anywhere that there's metal, you'll end up seeing stress fractures and strain marks that you have to contend with. It also happens in composites as well. Usually it's bolt hole elongation is kind of like a strain injury that happens to those things, where instead of cracking, what it does is it compresses the hole through the excessive, particularly shear force seems to be the most common culprit there. until the bolt hole gets too wide and it can't hold on anymore. Wood, when we had wood aircraft, that was a serious thing that you would go through, and you would check the width of bolt holes, because the bolt holes eventually over time, just like composites, wood will compress down. If you take a hammer and you a 2x4 and you just beat on the 2x4, eventually you'll get these little dimples that are being made. That's because you're compressing that wood. That's a strain, injury that's happening to that material, and it is no longer useful. So those are the forces that will act on the metals that we're about to talk about. So keep those in mind as we talk about the different attributes of metal and how they harden them and anneal them and do all the things to try to prevent them from giving way to some of the more negative or negative attributes of metal, and they try to enhance the more positive attributes of metal. Okay, before we start working on the different types of metals that we're going to use, let's just talk about metals in general, and so that way we can establish kind of a vocabulary to really analyze and understand metals from here on out, because it will make a difference with some of these traits and some of the materials that we end up using or not using in different applications. First off, let's look at hardness. Now, a metal's hardness is its ability to resist abrasion. So you think about a diamond. A diamond is like the hardest substance that we know of. What scratches a diamond? Only another diamond, if that. But a diamond can scratch anything. That's because it is extremely hard. If you had a shield, one of the things you'd want a very, very hard shield, because nothing's going to be able to penetrate it. It does the damage to something else rather than it taking damage. Another one is strength. Very, very important one. Strength basically denotes on how much the metal can maintain its form under stressors. So if you think, if you ever look at a 747's wings when it's fully loaded, about to cross the Atlantic or the Pacific, it is like the wings are almost on the ground. It's just loaded down with fuel, right? But then whenever it lands and all that fuel's off, it's back to its original shape. It's ready to be refueled and flown again. That's because the wings are very, very, very strong. Even though that they may give under the weight, they don't deform. They simply snap back and they're ready to go again. Okay, brittleness. You've ever seen like a blacksmith take a super duper hot piece of metal and dip it into motor oil, and then it kind of flames up on them? Well, the reason they do that is that they're introducing carbon into the metal, and they're making the metal more brittle. Depending on what you're going to use that metal for, you may want it more brittle or less brittle or whatever. Brittle, if you think about like a cookie, is very, very brittle. You break it and like all little bits and pieces kind of flake off. As opposed to if you go to Walmart and get one of those oatmeal cookies that are really, really nice and soft, they're not brittle. They're very, very elastic. They don't break and explode like that. And so depending on what you're trying to do with that metal, you may want it more brittle or less brittle, more elastic or less elastic. It just depends. But that is a factor to consider. Conductivity. Conductivity is another big one. So we talked a little bit with electricity and carbon fiber. Well, I mean, metal is used in wires. We have aluminum wires and copper wires because of their high conductivity of electricity, but also conductivity with heat. We'll go back to our X-15. If the outside skin is a highly conductive metal, then that means that like where the pilot's going to be sitting, if he might have other metals that are touching that metal, if they are highly conductive, he's going to also get hot. On the SR-71 program, the pilots famously heated up their lunch on the dash of the plane because the glass would get so hot that it would actually cook their meals for them. They'd reach up there and they'd pull it off because that's how fast they were going. All of those little traits all speak to conductivity, both of heat and or electricity. And that's something that it's not a good thing or a bad thing. It's just a trait of a metal. And maybe you want to use this type of material here because it's very conductive, or maybe you don't because it's very conductive, or maybe you want to use something that's very non-conductive in a very specific place. Either way, you need to know these traits and you know how they kind of give and take. One we haven't talked about yet is, to at least a high degree, is thermal expansion. Anytime that metal gets hot, those atoms start getting all excited and they start pushing outwards. Now, depending on what the substance is that we're talking about, they'll expand or contract to different degrees. So if you think of a balloon, well, like you leave it out in the sun, it'll get hot and it'll inflate up. You put it in the cold or at a high altitude, and it'll contract, back down. If you do the same thing with, say, a aluminum coffee cup, hot or cold, unless it's extreme, you won't see a difference between the two of them. Now, there are differences there, but they're very, 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 very small. They don't have a high thermal coefficient, or thermal expansion coefficient, to cause that big swing. It's very, very controlled. A lot of times, the metals that we use won't, but sometimes you need to think through, like, hey, look, this metal has a thermal expansion factor that's significant to what we're doing or what application that we're employing with. And that's something that you need to consider whenever you're making a choice on metals or affecting a repair. Okay, so what fusibility? Fusibility basically means what's its melting point. Now, this is something that it matters because when we'll talk about this a little bit more with thermal expansion, as things get hot, you don't want it to get super ductile, so that way it permanently disforms. Now, for years, this was not really a concern, but now we're seeing the reintroduction of supersonic flight with Boom Supersonic. You're seeing a lot of talk about hypersonics. Anything going over Mach 5 is hypersonic, and then all of a sudden thermal expansion becomes a key player, because whenever you're going that fast, the amount of friction over the skin of the aircraft can cause it to be deformed and stuff. So whenever you're making design decisions, you need to think about the fusibility of the metal that you're choosing, because that could have a major factor. If you build the perfect plane on the ground, you get it up to Mach 5 at 80,000 feet or whatever, and it just basically melts on you. The X-15 famously had to be painted with a blader paint to help deal with some of this. That it would that paint would get hot and flake off, and it would land as a pink plane. It would take off black and land pink because all the ablator paint was gone. That is an example of fusibility. Okay, let's talk about toughness. Toughness and hardness are very, very similar. Toughness basically means that the metal can withstand a lot of wear and tear without it being tore apart or broke down or ripping or tearing to a permanent state. We want our aircraft to be tough, especially primary training aircraft, because they're going to take a beat down. You don't want to necessarily give something that's really, really fragile to somebody who doesn't know how to fly. You want to give them something that's extremely tough, like a Piper Cherokee, that you can just slam it into the ground over and over again, and it just pops back up and is ready to go again. That comes at the expense of some of these other traits, but it is extremely advantageous for a primary trainer. Now, you wouldn't see like a U-2 spy plane being that tough. No, it's very delicate, and it's very built exactly for the way that it's going to be used. And it's being handled by some very professional pilots, so not as tough. But it is fantastically less dense than, say, like your Cherokee or a similar aircraft. Ductility and malleability are very, very similar in a lot of different ways, whereas being ductile allows you to permanently change the shape. Malleability more says that you can change the shape without it bending or breaking. Copper will actually tear depending on the thickness of it. So it's something to keep in mind. Elasticity. Elasticity, we all have it in our clothes, elastic bands, right? So it's something that it can go out to a certain degree and then snap back. So we're talking about the 747's wings. That elasticity in that metal allows it to come back to the shape that it's in. It's also part of the design of the plane to be able to make those big swings, but without the elasticity of that aluminum, the design wouldn't work. So another key trait is density. This kind of goes back to carbon fiber. Why do we like carbon fiber so much? It's very, very strong, but it's not very, very dense, so it's very, very lightweight. Density is something we want to take into consideration as we consider different metals for different projects, or analyze what metals are where on an aircraft. Because the more dense something is, the heavier something is, and weight. If you remember back to our four forces in flight, weight just increases that gravitational pull, or like is more susceptible to gravity on an object. And so we want to minimize density if we can, but not at the sake of some of these other traits, depending on where it's at on the aircraft. Malleability. Malleability is really important. We want to be able to mold and shape metal into being the shape that we want. Now, it makes sense why an aircraft is a tube in shape. It's easy to pressurize. It's very aerodynamic. It flies. Years of experimentation have basically resulted in that shape being chosen. But if we weren't able to make aluminum malleable, we would never be able to achieve that shape. We would just simply have, like, I guess, a big sheet of metal or a big wad of it that we're throwing wings on, and it would never work right. So malleability, the workability of that metal is really, really important. All right, there are largely two types of metals that are used on aircraft. There are some others, but generally speaking, there's two main families: ferrous metals and aluminum. Now, ferrous comes from the periodic table of elements. Ferrous is Latin for iron. So there are all different types of iron alloys. Now, this may sound weird to you, but you're very familiar with these. If you've ever seen anything rust, that is a ferrous metal. Here's a magnet. Ferrous metals will stick, or magnets will stick to ferrous metals rather. One of the key features of ferrous metals, one of the ways that we'll end up looking for corrosion, is the orange-brown oxidation that will form on them that we know as rust. There's all sorts of types of ferrous metals that are alloys. They're carbon alloys, or carbon steel alloys, magnesium steel alloys that are used throughout all of aviation, both on ground support equipment like this, on your aircraft. A lot of the cases of engines that we'll work on, the recip engines, are made out of ferrous materials. That's something that you'll get very familiar with, and you'll be very used to working around ferrous metals. Now, steel can be hardened by plunging it into things. You've all seen the pictures where the blacksmith is working, the steel is super hot and orange, and then they plunge it into a salt water bath or motor oil or whatever, and it causes it to harden up. The downside of that is that it also makes it more brittle. So the more brittle you make it, the harder it becomes. The way to soften it back up is called tempering. Other types of hardening is case hardening. This usually breaks down into carburizing or nitriding. Basically, carburizing and nitriding is just adding different adding different things to the steel to harden it up in different ways. Both have their strengths and weaknesses, just like all the other things that we've seen. Annealing is the opposite of hardening. You're making the steel softer and making it less brittle. Normalizing, the steel removes the internal stresses set up at heat treating, welding, casting, forming, or machining. It's just returning it back to baseline rather than taking out all the work that you put into it. When steel is hot worked, it goes from the heating period to the soaking period to the cooling period. So the steel has to be monitored to increase in temperature at a certain rate over a certain period of time, to make sure that the right internal structure rearrangement is happening inside of the steel itself. Then it has to soak for a certain period of time. Once it's soaked for a certain period of time with a constant temperature, then we know that certain molecular changes have happened. And then it has to cool down at a certain period of time at a certain rate. If any one of these is different, you get a different result of steel at the end of it. And so you want to be very, very precise whenever you're doing all this metal working. Now, the other type is aluminum. Notice that it doesn't, the magnets don't stick to it. Some ferrous metal right there. Now, aluminum will not attract a magnet, and it also corrodes totally differently. And there's all different types of aluminum alloys as well, used for different applications due to the different attributes that it has, both ductility, conductivity, thermal expansion, malleability, you name it. Those different alloys are mixed together to capitalize on the right set or right combination of those attributes depending on wherever they're used. Now, aluminum in its pure form is far too soft to really be used for anything for the most part. And so it has to be mixed with other metals to raise its strength. Once you get to that higher heightened strength, then it's very, very useful. Comes at a certain expense, because by putting other metals into it, you add traits that you may not necessarily want. But over time, we've been able to minimize that mixture, or the downside of it at least, and maximize the upside. Okay, aluminum can be broken down into two basic categories of alloys. One is wrought alloys, and the other one are casting alloys. Now, casting alloys you're probably familiar with. You've seen the big cauldrons of Mount Doom, and they're pouring metal and mixing things up, and they get a big steel bucket super duper hot, and they say, like, give me 2 parts of aluminum, 1 part manganese, and it all melts into a big deal. They stir it up, and then you pour it out into a big sheet, and then you have your casted aluminum. Ferrari, matter of fact, is famous for casting their own engines in sand. That you can go to their factory in Italy and watch them do this, and they will heat up aluminum, and they'll pour it into a sand cast, and it'll cool off, and they'll knock the sand off, and then you have an aluminum block to build your supercar off of. So that is cast aluminum. The other one is wrought, that's done through mixing metals through working them. So if you think about like a samurai's katana or Damascus steel, or they take metal and they flatten it way out, and then they fold it on top of each other and make multiple rolls. Imagine doing that, except for with different types of metal, and you're mixing them together that way, and that's a way to make a wrought alloy. Now, on these different dash numbers, or these different aluminum numbers, you might get 2024 dash and say like an H1. That H is it denotes the type of temper that it have. It can be F, O, or H. H stands for hardened, and you have different levels of hardening, so 1, 2, or 3. And I'll let you look those up and get the details of them. But just know that that's how you break down the kind of the part number for aluminum, which will become important whenever we get into sheet metal, and we'll revisit this in a lot greater detail. But essentially, your first 2 numbers will tell you what the additive is. The second 2 numbers will tell you what the level of that additive has been added to it. And then you'll have a dash number, which will tell you the temper of it. So H1 would be like hardened as casted, if I remember right. So that's the so what on aluminum part numbers. Now, wrought alloys have a 4-digit number system. The first digit will tell you what has been added to it. It may be manganese, it may be chromium, it could be any number, a bunch of different materials could be added to it to get the type of performance you want out of that aluminum. The last 2 numbers will tell you what percentage of aluminum is left in the last percentage of pure aluminum. So if you get a 1275 mix, never mind the 12 at the moment, the last 2 digits, the 75, tell you that it's 99% aluminum, all right? 75% aluminum with a 25% additive of something, say manganese or, yeah. Okay, every additive to aluminum gives it a little bit different. I'm just going to read some off to you. Copper is a principal alloying element in the 2000 series. Solution is heat treated, optimum properties equal to mild steel, poor corrosion resistance, unclad. Is usually clad with 6,000 or higher purity alloys, best known as alloy is 2024. So 2024 aluminum has a little bit of copper in it. 3000 series, manganese is a principal alloying element, which is generally not heat treatable. The percentage of manganese is effectively 1.5%. It's got moderate strength and has good working characteristics. It's very pliable. In the 4000 series of aluminum, silicon is the principal additive. It responds to a limited amount of heat treatment. Now, aluminum can also be heat treated, and the same processes and procedures can be enacted on aluminum just like they can with steel. You're going to get slightly different reactions from the aluminum, but the process is the same. Quenching, heating things up and letting it cool, and then when you to anneal something, you have to heat it up, let it soak for a certain period of time, and then let it cool in like room temperature air, steel air. And that's how you get annealed aluminum. And annealed aluminum is one of the most common types of metal that you're going to have to deal with. Annealed aluminum is what you're going to be working on with whenever we get to sheet metal. Now, aluminum rivets are something that you will end up using in this course. The aluminum rivets kind of break down into a couple of different alloy types that you can get it from. They are 1100, 5056, 2117, 2017, and 2024. Those are the general alloys that we will develop aluminum rivets from. Okay, so another metal that you'll come across is magnesium. Now, magnesium is extremely lightweight. It is very, very lightweight. Matter of fact, the OH-58 transmission is made of pure magnesium. Magnesium will also burn, and so if you get that thing caught on fire, it's something to put out. But it is used more than just there. It's used in all sorts of airplane parts where you need a super lightweight, very tough, hard alloy, but the weight is a serious factor. So if you took that 58 transmission, which is about that big around, and you made it out of aluminum or anything else, not only would it not work right, but it would be extremely heavy. Whereas magnesium is not heavy, so it's the perfect metal to be using in those applications. Okay, so another one that we need to talk about is titanium. Titanium is extremely hard and extremely expensive. You'll see titanium used in kind of high-end applications where it needs to be extremely strong, but also very, very lightweight. You can get titanium in either its pure form or its alloy, and it breaks into three categories: alpha, beta, and combined. Alpha titanium is just a good all-around titanium. It's not necessarily good for any one particular thing. Whereas beta titanium has been compromised and it's bendable. And then C is somewhere between the pure titanium, bendable titanium. It's a mixture in between. Most of the time, it's very rare that you'll actually see titanium out in the flight line or out even in a repair environment, but you could. The more advanced aircraft get and the more widely available titanium becomes, the more apt you are to see it, especially in future aircraft. Now, one thing about titanium that we should mention is that it basically doesn't corrode. It does corrode, but it's very, very slow and it's uniform, so you don't get like the isolated like pitting on like you will on aluminum, or like orange oxidation you will on ferrous metals. Instead, it's like an entire state of affairs for the entire piece. This makes titanium very, very attractive for aircraft that are very prone to corrosion. And so that's something to keep in mind when dealing with titanium, is that whenever you're inspecting a part, you can just go ahead and guarantee yourself that you're probably not going to find any corrosion on it. Another metal that is used frequently is copper. Copper gets used primarily in electrical systems. You'll end up seeing it on bus bars, you'll end up seeing it in wires, you'll end up seeing it on parts of circuit breakers. And the reason being is it has extremely high ductility and conductivity. So going back to our kind of traits of metals, copper is extremely useful for those types of things. It's not very useful for building a wing out of or anything else like that, because it will bend and flex and do all kinds of things that you don't want a wing to do. You want a wing to maintain its shape, not be bent up. So they're keep in mind copper. Copper corrodes green, so the Statue of Liberty is famously bronze whenever we got it, and then we basically didn't wash it off, I guess, and it corroded into being green, and now we just kind of like let it be green. Nickel is another one that you'll see. Nickel comes in two alloy types, Inconel and Monel. Mostly that they're gears or other sort of inner working parts. You generally don't see Inconel or Monel parts outside of some inner working type thing, like inside of an engine or a transmission or some sort of apparatus that has parts pieces that move. Something that we should say that the reason why we're going over all these different types of metals is one, that you can identify them and you can know that, hey, look, here's this part and it is titanium. Here's this part, it's magnesium. They have their different kind of attributes, and we use them for different things. And we go through all of that to basically say, don't substitute different metal parts. At least check the structures manual that comes with that aircraft to make sure that it is substitutable. Reason being is that the engineering was done based on that material science for that part going into that application. There's corrosion things that you need to be concerned about with it. There's strength and wear and tear and all sorts of things that you need to be considerate of whenever choosing a metal to use somewhere on the aircraft. So don't just willy-nilly say, oh, look, here's another widget that we can just replace with this widget because it's convenient. We can rob this part from this plane and put it on that plane or something like that, because 9 times out of 10, if they're not the exact same metal, there's going to be some sort of hazard that you just introduce into that aircraft. Where a lot of this will come into play is that if you weld on the aircraft or somebody else is welding on the aircraft, you might get some of these effects of the metal has been worked, and so you might have to renormalize the parts pieces around the aircraft if you can't just simply outright change the part that had been welded on. Now, you shouldn't ever have to do this as an airframe power plant mechanic, but if you're in some sort of fab shop or you go down the structures route and you start working on, say, a spacecraft or something like that, this will all become very, very relevant to you. But for the majority of us that just are going to fix airplanes like the one behind me, you shouldn't have to be worrying about cold rolled steel or hot soaking or anything else like that.